the enforcement module will intercede. He'll read a copy of that kernel module as well as the profile, and then he'll do the hash, taking into account the relocation addresses. If they match, then he'll copy that code into the shadow memory, and everything will be able to run as you would expect. So at this point, we have a system constructed that can prevent rootkit kernel injection and can handle valid kernel modules. So improvements. There's a few problems that occur at the kernel level that didn't occur at the user level, or at least not in the same way. So at the user level, if an attacker tries to break into a process by using one of these memory errors, and I stop his attempt, usually a valid response is to just kill the running program. That's okay. It's not okay at the operating system level, because usually a good response to an attempted attack isn't shut down your machine. So for example, when you stop a kernel module rootkit on Linux, you get a screen that looks kind of like this. And this is a kernel oops, which is the kernel telling you something really bad happened. Now the system actually continues to run, but you've lost some allocated memory that you can't get back. And just in general, it's really not clean. Windows, when you stop a kernel module type rootkit, gives you a blue screen and halts completely. Well, this is totally unacceptable. So we need to be able to handle this. Well, one simple approach is instead of routing that instruction fetch down into the shadow memory where there's nothing, and that's what causes that, not nothing but all zeros, which cause those exceptions, what if I were to route it to a piece of my own crafted code that just says return -1? Well, the reason that I chose return -1 is because most of these rootkits are being initialized as kernel modules, and then the first thing that the operating system does is call their init function. Well, if the init function just returns -1, the operating system will assume that some error has happened, and it'll recover gracefully. So in the Windows example, instead of getting a terrible blue screen, I get a nice error message that says unable to load the driver. Well, that's nice. It's much more clean, and my system doesn't crash horribly. So that's exactly what we're looking for. It's much more elegant. So that's how the system works. The question is, how effective is it? How well does it perform? So I prototyped this in both QEMU and VirtualBox. And I implemented that kernel module profiler for Linux 2.4. So I ran all my tests on Linux 2.4, Linux 2.6, and Windows 2000 XP. So Linux 2.4 has full support. The other two operating systems have more limited support. Linux 2.6 because I didn't take the time to do the module profiling. It wasn't important for these results. And Windows 2000 XP because I'm really not sure how its driver functionality works. So for those two operating systems, what you have to do is boot the system to a usable state and then turn on the protection. For Linux 2.4, you're protected from the moment that you start booting. So effectiveness, another really big chart. What I want you to gather from it is that I tested 24 different rootkits that span Linux 2.4, Linux 2.6, and Windows 2000 and XP, and was able to stop various types of attack vectors, was able to stop all of the rootkits without any trouble. Performance is probably a more interesting question for this. What is the performance like? So for the kernel compiling test, the performance, well, okay, I ran 4 tests. One was compiling the kernel, which required me to just compile the kernel and see how long it takes. Another was inserting a module. The question was, how long does it take to insert a module into the running kernel? And then the Apache throughput test again, and then Unix Bench, another one of those benchmarking programs. So 3 of the 4 tests ran at well above 97%, which is extremely good performance. So the blue bar represents an unmodified version of QEMU, and the purple bar represents my modified version. Now the insmod test was a little bit slower. It was down at 90%, a little above 90%. Well, as you can imagine, when you insert a module and you have to read it in and do the hashing and do the comparing and doing all of that, that actually takes a decent amount of time. So that's why you see that performance hit. But I'm not worried about it because there aren't that many workloads that involve adding and removing modules all the time, and that's all they do. So that's really not of concern. So, a summary of my work and what I'm presenting here. Most commodity systems are going to be using von Neumann architectures, and they're inherently vulnerable to code injection attacks. But it doesn't have to be that way. Not all memory architectures are. Things like the Harvard architecture are actually immune. And it's possible to construct a new architecture on top of von Neumann that's immune to that code injection problem. And at the same time, I've just demonstrated that it's usable at both the user and kernel level. It's effective and has reasonable performance. So if you have any questions, I'd love to try to answer them.
Any questions? I have one. There's one, I can still see one possible attack, or that it's not quite code injection.
Mm-hmm.
But if somehow an attacker were able to modify the relocation, or the linking process of a module, could she install a fake address so that when that dynamically loaded module was executed, it would go someplace else other than where it's supposed to? Would you catch that?
So what would be the goal? Like, where would you be sending it to?
That would be the hard part, is you'd have to find some place you could send it to.
In the existing code base, basically?
In the existing code base, or was there anything to prevent it from going outside of the current kernel memory? Executing outside the current kernel memory and yet still retaining kernel privileges?
Sure. So there's kind of two approaches to the attack you just described. One approach is to say, well, what if basically the attacker finds some way to get it to execute arbitrary code that already exists, and he crafts that to be something malicious? And that's an extremely valid attack, which for a long time actually wasn't too plausible until just recently, when all of a sudden there was a very good paper that described how to make that extremely plausible. So you're right, and that's an approach that I can't handle right now. It's something that we've looked at in some of our future work by trying to think about control flow integrity and such. But yes, I can't handle that particular approach. So the other one you described is another potential attack vector, which basically says, what if I were to, say, put my code somewhere else in memory, maybe in user space or something, and try to get the kernel to jump to it through some other malicious means? Well, and the important distinction is that any instruction fetch that's going to be executed at the kernel's privilege level automatically gets routed to the shadow memory. So if you install new code, no matter where you put it, you're not going to be able to fetch it. But it does raise the question of, well, what if I were to have part of my malicious code run at user level? And so that's a potential too. You could imagine this really convoluted rootkit where certain parts of the kernel code then drop to a user level privilege and run and then go back up when they're done. The problem there is, well, I do think you could construct that sort of really strange rootkit. I don't think you could do it without having to modify any existing or add any existing kernel code to help you along.
There's a problem. You need to find instructions going on within the kernel, or you need to find a sequence of bytes in the kernel which would do what you wanted.
Right, that's part of it. And there is work that moves along those lines, but it's still, it doesn't, you still can't construct the type of attack I just described with it.
Other questions? Well, I'd like to thank Ryan for...
Thank you.
Look forward to having you all here next week. Well, I'll tell you what we have coming up, but I don't have the seminar list.
I think it's Symantec next week.
Oh, yeah, we have a visitor from Symantec.